And we're back. Welcome back and happy Thursday. Today, our focus will be on methods and considerations for visualization. Before we begin, some of the administrative bits, the reading. By the 28th of January is section 8.3, which pages 223 through 233. It's not a lot of reading, but please make sure you are keeping up. Project 1 will be due on Tuesday, the 26th of January at the usual 11:59 and 59 seconds, 1 second before midnight. So, seeing is believing, and that is certainly the case when it comes to your data. Whenever you are furnished with a data problem and you want to do some analysis on that data, the first thing you need to do is take a look at that data. And what you see in the data will help inform the choices you make about the analytical techniques that you might enterprise to use on that data. And so this is an interesting graph. This is a pizza chart. It's a geographical map of the continental United States, and marked in this map is a color-coded depiction of the major pizza chain in each area. So this is a real chart. And when companies, or chains rather, decide to place a branch or franchise in an area, they do lots of research about the demographics because they want to know, well, answer the question, will people there buy this pizza? So they look at things like home ownership, number of college students, the age distribution of people living in the area, how much income they make, because people without a lot of disposable income don't buy certain products, for example. And so here we have in our legend that identifies what pizza chain we're referring to. We have Chuck E. Cheese in purple up above. We have CC's Pizza, which I haven't really heard of before looking up this chart. Domino's, Godfather's Pizza, which I believe the late Herman Cain was an executive there. Little Caesar's Pizza, Pizza, Papa John's, which I don't know too much about, Papa Murphy's, which I know nothing about, Pizza Hut, and Sbarro, which I tend to only really see in shopping malls and occasionally rest stops on the highway. But nonetheless, here we have a map of the continental United States. And if you look along the west coast here, you have Washington State, you have Oregon, and then you have California. You mostly see Papa Murphy's on the west coast, from right around the Bay Area going north into Oregon and western Washington. Then, as you go further towards Southern California, LA, down to San Diego, Baja California, you see more Little Caesars pop out. And then as you get really close to Baja California, you see some Pizza Hut. Now, it's interesting here when you go into Four Corners, Utah, Nevada, Arizona, and New Mexico, there are large gaps here. There's a pizza desert, so to speak, in those areas. Also, if you look around Idaho, there's a little bit of a pizza desert. So one question you might ask yourself, why is there just a blank spot there? Those poor people, they don't have any pizza. But that might not be the case. Given that you have a lot of desert in the Four Corners region, could it be that there's no population? Interesting. So if you were investigating something related to pizza sales, maybe you were selling tomato sauce for pizza or cheese, mozzarella for pizza, you might want to know what's the reason for not having any pizza shops there. So things like geographically registered or geographically referenced or indexed visualizations are very good for telling you things about locations within a geography, within a country or area. Likewise, if you go to the state of Maine, there's a big hole here. We don't have really much pizza. So the question is, do they not like pizza? Or is it that there aren't that many people there? Why is that the case? Interesting. So now, as we go across from the West Coast, across the Midwest, down into Texas, Well, in West Texas, we see a lot fewer pizza, but in East Texas, oh my goodness, you see lots of pizza dominated by red, which is Pizza Hut. You do have a smattering here of Domino's and some Cici's, but it's primarily you see some red here. And as you get close to the Mexican border, you see mixed in a little bit of Little Caesars. Interesting. So let's go direct our attention here. We see a lot of Papa John's in this region. So we have Tennessee, we have north of Alabama, Georgia rather, and Louisiana. And then when we go to Ohio here, that looks like Ohio. Yes, that's Ohio. We see some Domino's. And then if we go down to the West Coast, here, this is Massachusetts. We see a large wall of Domino's of blue as you go from Massachusetts down through New Jersey, Delaware, into D.C. area. You see a lot of Domino's. And it just so happens your Domino's line seems to coincide, this blue, with the Northeast Regional for the Amtrak train. Very, very interesting. On the other side of this Domino's line, you see a wall of red primarily. That's Pizza Hut. And so it's interesting that you see lots of different concentrations of different pizza franchises. Now, if we go here to, it looks like Michigan, that's Michigan, you see a lot of Little Caesars. They really like Little Caesars over there. But nonetheless, this pizza chart shows you concentrations of the dominant pizza franchise in various locations throughout the country. So armed with this sort of information, not only do you know something about the pizza shop, indirectly, you can say something about the populations of those areas based on the demographics associated with people who typically avail themselves or partake of various types of pizza. So here's another map. Now this other map, this is a population map, not a pizza map, and it is a so-called relief map. Again, it's geo-registered, meaning that it's relative to a geography map of the United States plus Puerto Rico, the territories. Here we have the continental United States. We have Alaska, Hawaii, which aren't south of Texas. They're really out in, Alaska's way up north, and Honolulu and Hawaii is out in the Pacific. But they just put them next to the continental U.S. just for the visualization purposes. That's really important to remember. But if we look at this map, well, whenever we have a large population, the size of the population is represented by a relief point that's at a certain height. And this is our legend here. It tells you about the population density per square mile. So if the population density is lower, it gets closer to white, and then it turns yellow, brown, and then red, and then this deep red, brownish red is the highest population density. So we have a bunch of major cities marked on this map. Billings, Montana, over here. Salt Lake City, Utah. Las Vegas, Nevada. Phoenix, Arizona. Denver, Colorado. Cleveland, Ohio. Boston, Mass. Here's Maine. Portland, Maine. Largest city in Maine is right about there. And then if you look here, let's flip back to the other map. The Domino's line we talked about mirrors the northeast line for the Amtrak, the Northeast Regional. Well, if we go from Boston to D.C., well, you'll notice here is a particularly high set of densities associated with cities and locales along the Northeast Regional Rail. Now, Northeast Regional Rail is among the most highly trafficked Amtrak routes in the country. And that makes sense because there are a lot of cities and a high population density, and people tend to use trains to get around more easily where there are dense populations. But that being said, let's look at some of the individual spikes here. Well, this is New York. New York is the most populous city in the country. Okay. And then you have Boston, a spike. Here you have parts of New Jersey and Washington, D.C. Over here is definitely Chicago, Illinois. And then we have Los Angeles, California. We have Silicon Valley down over here. You have San Francisco, and then you have Seattle, Washington, Denver, Colorado, Phoenix, Arizona has some peaks, Las Vegas has some peaks. But if you look here, so if we look back to this hole here in Las Vegas, Nevada, and flip back to the previous slide, we see that that hole in Las Vegas, Nevada, where there's no population or very little population, must be desert, we see that there are no pizza shops. And so that coincides very well and explains why there are no pizza shops there. Let's look at other parts of the country. If we look at parts of Maine, northeastern Maine, we see that there's very little population there. And we also see that there are very few pizza shops. So we can actually take the information from the population map, the relief map, and use it to explain what we see to a very accurate level of detail, to explain what we see in the pizza map. So let's go forward. And this just says when you have data, the first thing you do is you look at it. You try to understand what the data is telling you, and you can take multiple sources of data to paint a very accurate picture of what it is you're trying to say. So let's take a look at different data types. The world is full of all sorts of objects, and you give these objects labels. Labels like cat, dog, truck. And these labels describe distinct categories, hence the name given to these types of data, categorical variables. So let's say you had a variable called animal. An animal could be a cat. Animal could be a dog. Cat and dog are so-called categorical variables. Rather, animal is a categorical variable. It takes on categorical values. They're objects that have labels. Now, some categories have no natural ordering. If you're given the picture of a cat and a dog and you want to sort them, you can't really put one before the other or the other before the first one. These are so-called nominal variables. Now, of course, you could certainly alphabetize them by their name, but the actual picture itself, you can't really find a natural way to order them. There are other categories that have natural ordering. These are called ordinal variables. Let's take, for example, the movie ratings for appropriateness for certain ages to view the content. You have rated G, PG, PG-13, R, and NC-17 in order of the inappropriate material. G is for the youngest audience, and NC-17 is for the oldest audience, and you can naturally order these categories. So these sort of categories are called ordinal. So we have categorical and we have ordinal. They're both categories, but one has a natural ordering and the other does not. So let's take a look at numerical data, so-called quantitative data, things like measurements. If we look here to the schematic of a home, we have 48 feet 6 inches. That's a measurement. These are numeric values, and they can be both measured and ordered naturally. Let's take a look at these specifications for water tanks. Well, you have a 1990 gallon, 1,000 gallon, 500 gallon, and so forth. Well, this variable capacity about the number of gallons or the storage capacity of these water storage tanks, these are quantitative. They can both be measured and they can be ordered. So these are so-called quantitative variables. So there are two types of quantitative variables you can think of. One is called discrete. Discrete variables are so-called countable. You can put them in one-to-one correspondence with a set of naturals, and we talked about that last semester, what discrete means. And there's also continuous. They're uncountably infinite, and we talked about what uncountably infinite means last semester. So let's take a look at some nuances for each of these. So here we have three graphs, And it's really important whenever you are presenting a graph to help your audience understand what the axes mean. So we have a horizontal axis along the bottom, and then we have a vertical axis along the side. Now you notice here I didn't say XY axis. I said horizontal and vertical, and that's on purpose, because these axes might not be Cartesian coordinates. You say XY for the simple case for two-dimensional Cartesian coordinates, but more generally you say horizontal and vertical. So in the first frame, we have a horizontal and vertical axis, and along the horizontal axis, we have a categorical variable, namely gender. So there are two categories, male for men and female for women. Now, of course, on the vertical axis, you have counts, and the height of these bars represent the number of counts. And so here, we might depict in a graph like this the number of men employed by some company, X, and the number of women employed by that company. So here we have categorical variables, the gender, and here we have quantitative values, and these are countable, they're discrete. Let's take a look at the second graph. Here along the horizontal axis, we have a car's age in years. Now in this particular case, it's a little different. Yes, a year is a quantitative value, and in this case, it's discrete, it's countable, but it's being used as if it were a category, a 5-year-old car, a 10-year-old car. Along the vertical axis, we have a car price, and that is quantitative, and it is discrete. They're whole numbers. You can draw one-to-one correspondence with them when they're real numbers. So let's take a look at the third frame. This third frame, we have years. Now, year is a number, and you think they're quantitative and they're discrete. But if we look at how it's used, they're used like categories. The year 2010 is a category, the year 2015. They're not being used as numerical values. And then we also have their counts. Those are numerical values, they're quantitative, and they are discrete. And so there are some types of instances where you have nuances, and these nuances concern your variables blurring their definition. You have numbers, numerical values, sometimes treated as if they were categories. So let's take a look at a bar chart. Now, a bar chart you use typically to visualize counts and accounting, if you will, for categorical variables. You have a bar for each category. So in this particular chart, we have the number of children born in each season for a particular family. And so if we look at the data, we have one child was born in spring, 2 in summer, 2 in fall, none in winter. Along the horizontal axis, we have the categorical variables for season, taking on category values, spring, summer, fall, winter, our seasons. And along the vertical axis, we have our counts. Those are numerical values. They are discrete, quantitative values. And so the number of children, 0, 1, 2, or 3. And if we look at the height of the bar relative to the vertical axis is the number of children. So we have 1 child, 2 children, 2 children, 0 children. And so this is a typical bar chart, and it is often used to visualize counts for categorical variables. So bar charts are also used, or can also be used, to illustrate relative relationships or differences. In this one, we have, if we look at our data, we have companies, the names, and the number of employees they have. And in the bar chart along the horizontal axis, we have our categorical variable company, and it takes on values corresponding to each one of the companies, Walmart on through Hewlett-Packard. Along the vertical axis, we have the quantitative variable, their counts, the number of employees, and these are discrete. And the height of the bar is the number of employees for each one of those companies. Now, in this particular case, we have a bar for each one of the companies, but this graph, you'll notice it's also sorted in non-increasing order. We go from biggest on through smallest. And in doing so, we can very quickly visualize and draw comparisons or differences between the various companies. We know right away Walmart has the highest number of employees. Walmart's number of employees is about 4 times the number of employees, a little bit more than 4 times the number of employees at Yum Brands, which owns Taco Bell and KFC and a couple of others. Likewise, we know that among all of them, Hewlett-Packard employs the least, and that Home Depot is not very far off from the number of employees at Hewlett-Packard. And so bar charts can be very useful in drawing comparisons. You can also use a bar chart to depict relative frequency. Now, this chart is the same information for that family we had 2 slides ago, only instead of having counts, we're going to have proportions. So what do? We take all of the counts, and I'll direct your attention to the legend in the inset, and we have the number of children born in each season, spring, summer, fall, winter. That's 1, 2, 2, 0. We divide each count for each season, each outcome of the categorical variable season. We divide it by the total number. So 1 plus 2 plus 2 is 5, so then we divide 1 by 5, 2 by 5, 2 by 5, 0 by 5. We get 20%, 40%, 40%, 0. So now when we draw the bar chart, yes, we list our categorical variables for the season, spring, summer, fall, winter, along the horizontal axis, vertical axis. Instead of having counts, we're going to have that relative frequency. So this, consequently, is a probability distribution over the seasons. But as a bar chart, we talk about this relative frequency as giving you these proportions that you can now draw comparisons of how between all the different seasons and how many children are born in a particular season for this family. So let's take a look at the pie chart. Now, the pie chart also depicts relative frequency, but it visualizes it differently. Instead of as proportions normalized, drawn in a bar chart, it depicts them based on the size of the slice of a pie relative to other slices of a pie. So a pie represents the whole, 100%, and then each slice is proportionately sized relative to the amount for each of the categories that might be taken on. And so this particular graph talks about, and it's from the Bureau of Labor and Statistics, the percentage of the day spent in hours by students for various activities. And so 8.7 hours, which is about a third of a day, they spend sleeping. And you'll notice here this wedge of the pie for sleeping is roughly a third of the entire pie. And so this very quickly gives you a sense of the relative amount, the relative proportion associated with each one of the activities. And in fact, you could take this bar chart, normalized bar chart for the Jones family, and turn it into a pie chart, and it gives you a very nice visualization. So let's look at the scatter plot. Now, the scatter plot is used to depict the relationship between 2 or 3 variables. Now, it's hard to go to higher than 3 variables because it's hard to plot 4 dimensions or more on a 2-dimensional slide or screen. But nonetheless, each axis represents a different variable, and the coordinate with respect to each axis is that variable's value. So here we have a 2-dimensional axis. We have our horizontal axis, or x-axis, and the vertical axis. And each one of these tick marks along the axes represents the variable's value. So we have 2 variables, the x variable and the y variable, and each point drawn in the scatter plot, its projection along the x-axis represents its x value for the variable, and projection along the y-axis represents the y variable's value. And so in this case, x variable has value 3 and y has a value of 5. Now, of course, with the scatter plot, it allows you to look at the relationship between 2 variables. So here's a scatter plot, and this particular scatter plot is used to depict a college football team's ranking relative to a head coach's salary for the team. Along the horizontal axis, we have head coach salary. There's $2 million, $4 million, $6 million, $8 million, so forth. And along the vertical axis, we have rank, that going from rank 1 going up to rank 140. Now, in this particular case, and this is really important when you're interpreting a graph for your audience, to explain to them what these numbers mean. So as we go to the right along the horizontal axis, salary increases. So to the right means a bigger salary, more money. And then as you go further down, it means the team is ranked more highly. So rank number 1, you are the best team in the nation. Rank number 140, you are not the best team in the nation. So as you go down, the team improves. It's a better team as you go down. So smaller is better with respect to the vertical axis. Okay, so if we look at this, we see some points, and we see one point here. Let's see. You're about $2 million in salary, and your rank, it looks like it's about 15, 16 or so. And here we see $7 million salary, and your rank is number 1. So what it tends to seem like is that as your salary goes up, the rank of the team gets better and better, meaning that you get closer and closer to 1. Let's test this out. Let's choose a point over here. Well, the salary looks like it's about 500, 300,000, and the rank looks like about 128. So that seems like it plays out. So we have the scatter plot, all these points, and each point's projection along the horizontal and vertical axis represents a variable measurement. In this case, we have salary along the horizontal axis and rank along the vertical axis. So this point here would be 7 million as the salary and 1 as the rank. Okay, so now what we can do is we can take scatter plots and draw a trend line using something called regression, and we'll cover that during the semester, and use the slope of that trend line to describe to us the relationship between the two variables represented by the vertical and the horizontal axis. So if we do that for this particular scatter plot concerning head coach salary versus rank, we notice that the line that best fits where the data points are in the scatter plot, the trend line, we notice that it's slanting or sloping downward. So that's what we referred to when we talked last semester about correlation, right? We said it represents the unit step increase or decrease in one variable and the commensurate amount of increase or decrease in another, the measurement of the coupling between two variables. So what this says is if you increase, go to the right, the coach's salary, you improve, i.e. decrease, the rank. That's what a downward sloping line means. An upward sloping line would mean the converse. But here is downward sloping. So that means in general, for the points in this graph, if you increase salary, the rank improves, gets closer to 1. So let's take a look at the line chart. So here we have some stocks, Apple stock, and we have periods that are marked 1 month apart, so roughly 30 days. And we have all those measurements throughout a year going into the following year and what the stock price was over that period of time. So we have the stock price at the close of the trading day. So at the end of the day, what was the stock price when trading stopped? Okay, so here we have a bunch of plots here, and they are scatter plot, but it's in time. On the horizontal axis, we have the date, and the time increases, so they're sorted based on the temporal ordering in non-decreasing order as time gets later and later and later. And on the vertical axis, we have the share price in US dollars. So each point represents, for a particular point in time, what was the share price. So this would be the 2nd of March, 2015. The stock price was 129, for example. And so if we go in time from one point in the scatter plot to the next, to the right, we connect them together, points subsequent to one another, sequentially in order. We connect them to one another with a line segment. And what this line segment represents is the general direction of what the stock was between these 2 dates. So you can almost assume, okay, it must have been around this value halfway in between. So this is a line chart, and what a line chart's purpose is, it depicts trends using straight lines to connect the subsequent points in a scatter plot. And this gives you the general direction of change over time. So we know between our first measurement here and our second measurement here that it decreased. From our second measurement to the third measurement, it increased, but at a smaller slope than the first segment. And then it increased, smaller slope, and then it started to decrease. And then decrease even more, decrease even greater slope, and then it started to increase. And so the slope of these line segments connecting subsequent points in the scatter plot give you this idea of coupling, but piecewise from one time instant to the next. You can also take this line chart and draw a trend line over the entire scatter plot. And if you do that, you get something like this red line. So we know that in the near term, for every 30-day period or 1 month period at a time, it might go down, might go up, might go up, might go down. But in general, over a long period of time, the trend is that it goes down. And so things like this are used with automated methods to try to advantage people in trading securities or stock and other derivatives from these securities to try to make money, i.e. try to predict what the market is doing. Okay. You can also use line charts to compare multiple data sets. For example, in this graph, we have categorical variable month along the horizontal axis, January, February, March through December, all 12 months of the year. And along the vertical axis, we have temperature. Now, temperature is real valued, it's quantitative and uncountable, but depending on the granularity you have, it could either be countable or uncountable, depending on the standard that you are depicting and how you're measuring. But that being said, we have 3 line charts. The green is Asuncion, Paraguay. The red is Tianshui, China. And the blue is Pueblo, Colorado, USA. Now, one of the things we want to ask is, okay, well, which city's temperature is most similar to Pueblo, USA? Maybe there's a crop or something you want to grow in Pueblo, and you want to see where else could you grow that crop, for example. So if we were to look at the trends over time, we see Asuncion, Paraguay. In January, it starts out high temperature, and then it dips around the middle of the year, June, July, and it comes back up in December. If we look at Pueblo, USA and Tianshui, China, we see that in January, the temperature is low. It goes up to a high around the middle of the year, June, July, and it comes back down in December. So if you think about it, well, Paraguay is south of the equator, and when you are south of the equator, your seasons are reversed. Our summer is their winter, and vice versa. So when it's summer in Asuncion, it's winter both in Pueblo and Tianshui. Moreover, the difference in temperature between Tianshui and Pueblo, many times it's not that much, but it doesn't get greater than about 9 or 8 degrees difference. And so that being said, if you look at them, while Pueblo and Tianshui are very close to one another in climate or temperature throughout the course of the year versus Asuncion. So if you had a crop that you wanted to grow that grows well in Pueblo, USA, a better choice if you wanted to grow it somewhere else would be Tianshui and not in Asuncion. Okay, so a line chart allows you to very easily compare multiple data sets, and each data set is a different color-coded line chart. And it's often the case in many pieces of software will plot using one of these different symbols in a different colored line. Okay, so MATLAB has different methods for how you present data. You can have it as a cell array, which is an array of arbitrary objects. Could be characters, could be numbers, could be strings, and so forth. You can convert these to categorical in MATLAB quite easily. You can plot histograms. It gives you a bar chart. You can use the API called bar, which is a numerical bar chart. Pie gives you a pie chart. Scatter gives you a scatter chart. And then you can do a scatter and a plot along with that scatter. It gives you a line chart, and it connects the lines for you between these scatter points. And so I'll leave that to you to look up in the MATLAB help documentation. It's quite good. And with that, we'll end there. That's all I had for today. Please make sure you're working on the project. And with that, please have a great weekend. I will see you all on Tuesday.